Hi everyone, happy New Year. Welcome back to Engineering Statistics. Because of the Christmas and New Year celebration, we stopped for almost 2 weeks of our lecture. So let's come back to our lecture. So we have learned about discrete random variable and also continuous random variable. And if you realize that we are only talking about the only affected by one parameter. For example, y equals to ax. We only referring to one outcome affected by one parameter variable. But in the daily life, there are a lot of conditions that the outcome affected by different variables. For example, your success CGPA is actually affected by based on your various subject in the class and your performance on your assignment, your quiz. It's not only just one subject, engineering statistics. And the other example is our car performance. So I bought a car, doesn't mean that I can perform the maximum optimum performance. It also depends on the replicant that I choose, depends on the fuel that I use, is that correctly? Imagine you have a good car, but you accidentally put a wrong fuel, you still not able to perform it well. Or in other words, it might fail, not able to move. So there are a lot of various other examples that actually our outcome influenced by other variables. So this chapter we are going to learn about bivariate probability, which affect by two discrete random variable or two continuous random variable, which also called as joint probability distribution. Okay. So back to this. So our learning outcome of this lecture is bivariate probability. We are going to learn how to, from the joint probability, how to find the joint probability, and from the joint probability to get back the expected value of each of the discrete random variable. Okay, and also we want to find it whether they are independent or they are dependent. So that we use covariance. And also, we also going to learn about, let's have a look, correlation coefficient. Correlation coefficient is to check whether your two variables are linear dependent. It doesn't mean that if they are, we will talk further on that part. Okay, so next. Okay, we will talk about discrete bivariate distribution first. Like the two previous lecture, so they have the same condition. The total, even though we have now two variables, the total probability is still between 0 to 1 because they join together. We assume that this is one case, and therefore the probability is 0 to 1. And the cumulative probability is distribution is always 1. Okay? Okay. So I would like to know, because there are two variables, I would like to know the probability distribution of each of them. And therefore, we call that as marginal probability. For marginal probability random variable, if you look at this, okay, so I would like to find the marginal probability of P, probability Y equals to 0. So what is that means is, okay, what is that means here is, you are actually, the changing variable here is X. Okay, can you see? X equals to 0 probability when Y equals to 0 is 0. But now my marginal probability Y is fixed. The changing one is X. Okay, so from there, I combine them. This is the marginal y equals to 0 and the probability 0.325. Well, I would like to find the marginal probability of x equals to 1. Okay, so what is that means is I log the x equals to 1, but the changing one is y equals to 0, 1, 2. Okay, is that clear? So when discrete random variable, the easiest one is you make another column and the row for n. You calculate when, if you look at the horizontal part, in this case, y equals to 0. Okay, and the second one is y equals to 1, y equals to 2. So the fixed one is y, the changing one is x. So in this case, this part is the marginal y. You can find marginal y here. And if you can find the marginal x over here. Remember, when I say I want to find marginal x, so means that your x is fixed, your y is changing, okay? And you're finding the total of it, all right? So, okay, give you an example. I would like to find, we warm up first to get a simple one first. I would like to find the probability of x equals to 1, y equals to 1. So it's quite pretty simple, it's 0.2. I would like to find x equals to 1, y equals to 2. So x equals to 1, y equals to 2. And I use green one, this one. Okay, simple. And next, px equals to 1. Okay, so now I would like to find the marginal px equals to 1. Therefore, I just join them, add them together. Remember, for my x, I fix, if you see this, and therefore I can get 0.3. Pretty simple, yeah? Okay, so next, I would like still let's learn about conditional probability distribution. Like the previous two chapter, we have the same condition, right? But because this is a joint one, so this is the first, this is the first, this is the second, right? And this one is the probability of the P2y, or the marginal y, okay? So, and therefore, you need to find the marginal first. For P2, y stroke x, this one first, and then given x, y happen. So, in this case, we need to find the marginal probability of Px. It's quite similar with the Bayesian theorem. Bayesian theorem. Okay, so let's go to the example just now. Find the marginal probability distribution Px for x. So if I want to find the marginal x, I know that my y changing. So this is the x fixed. Use a brighter color. So this is x equals to 0, y keep on changing. And therefore, I can find my Px equals to 0, Px equals to 1, Px equals to 2, Px equal to 3, 4, and sorry, this is 5. Okay, so you just write it in a table form, is fine. Next, find the marginal probability distribution of y. Same thing, remember, we are fixing the y in this condition. So on the horizontal part, the x changing, but the y is always fixed. So you just show it here. C, find the condition probability distribution x equals to 0 stroke y. It seems like y is not having any value yet, and therefore we need to find y at different value. So you can find the first one is x equals to 0, y can be equals to 0, x equals to 0, y equals to 1, x equals to 0, y equals to 2. So you just list down here. It's pretty simple. X equals to 0 is 0 given by x equals to y equals to 0. Okay, so yeah, the conditional x equals to 0, y equals to 0, 0, and your y equals to 0 is 0.235. Can you see here? Because this part is the marginal. Okay, and if you look at the equation, the C part, px equals to 0, y is 1, right? 0, px equals to 0, y is 1, okay? It's px, remember, px equals to 0, y is 1, it's 0.2. Can you see here? 0.2, right? And in this part, I'm looking for marginal py equals to 1, which is 0.415 over here. And therefore, I use this and put it here. And this one is here. Okay? Same thing here. I would like to find the P probability of join X equals, by referring to this equation, X, Y, and we know that X is 0, okay? Y at this condition is 2, so therefore I have 0.1, okay? And my P marginal Py equals to 2, I have 0.26. So by putting them, I can show the conditional probability distribution when X having the different condition, different value. Find the condition probability distribution y equals to 1 given that x equals to 0. Same thing. So x equals to 0, y equals to 1 is 0.2. And because now this part is x first, and x is 0. And therefore, I use 0.3 because my x equals to 0, the marginal is 0.3. Okay, pretty straightforward, yeah? Okay. Okay, so let's try. It might not, let's have a look. What is the probability that tire expert X will assign a grade of 2 given that tire expert Y assigned a grade of 1? So in this condition, seems like X and Y, they are expert tire expert. So we know that Y first, Y equals to 1 given N, then X equals to 2. It's saying given, right? So I quickly write it out. X equals to 2 and Y equals to 1. X equals to 2, Y equals to 1 is 0.1. Okay, then I need to find the marginal Y equals to 1. You remember Y equals to 1 is your Y fixed. Okay, so my Y fixed is 0.23. Okay, all right. So therefore, I have my answer 0.434. Okay, so we learned about the discrete random variable. Now we move to the continuous bivariate distribution. Like I mentioned to you just now, the probability of the join, whether discrete or continuous, they are always equals between 0 to 1. And the equation for them, because now we are involving two continuous random variable equation, it always start with integrate dx first, then dy. Why this happen? Okay. I have a look on a lot of presentation, YouTube reference. They always say dx first, not dy. Okay. The how to say that? The only thing that I can explain is when we look at the equation, it start with x first and y. And therefore, if we have a graph, okay, we are looking at the point that shaded below here. If you do the other way around, right, you are actually doing the integration on the green part, right? Which is we are not interesting on this part, because we are looking for the fx y. Is that okay? Okay, remember that, because I did huge mistake when I did my Form 6. I remember this always. Okay, and so if you want to same thing like the previous lecture, if you want to get the cumulative probability function to get back your probability density function, you just use the derivation. Okay, that's simple. Okay, so let's try this example. Okay, consider the joint probability function of the CRV below. So I would like to find the value of this. Okay, first you have to look at the condition. Okay, so and you always remember this is dx first. So and therefore my x is between 2 and 0. That's the only range I'm looking at. Then dy. My dy is I'm looking at 1 to 0. And you know what? Because of the first condition that I will mention, it's always equals to 0 when you looking at the huge only limited the considered space. The answer is always 1. You can try first later. Try to do the integration and prove it. Okay, so maybe there is a test or quiz saying that prove your cumulative probability function equals to 0. So you can just directly show the step. Okay, try that. Okay, this is an example for you. Unfortunately, my writing pad is some failure. So I would like you to try, and next Monday, we will discuss together. Suppose the joint density function for two continuous random variables, s and y, okay? So determine the value of constant c. So, okay, when you look at this, right, you have to first use this equation. Okay, and seems like your equation only have cx, there's no y. Doesn't matter, still write it there first, and then look at the condition. Remember, we start with dx first. It only covers 1 to 0. Y also 1 to 0. It's just coincident. They are having the same condition. Okay, if you having the different condition, 2 to 1, then you change it to 2 to 1. Okay, so then you can start doing the integration. First, ignore the dy, only finish the dx first, okay? And then use that to further integrate with dy. Okay, I try to use my finger. Let's see, I'm able to show you. Okay, so cx dx dy. This is 1 to 0, 1 to 0. Okay, first I do the integration first, and I know that the total is equals to 1. Am I right? So I integrate this part first, yeah? Let me write it for you. Okay, so c x2 over 2, am I right? And 1, 0. Okay, you still need to write the dy, but you ignore it first. Okay, dy. Okay, and then you plug in the 1, just the normal one, you know, c over 2. Okay, probably I change to orange. C over 2, you know why C over 2 gun? And then the other one is 0. Okay, and then dy. Okay, is equals to 1. Okay, so so we move from here. Okay, so now, okay, I have c over 2 dy 1, 0. Okay. So now we do the integration. So now, okay, because just now the orange part is we settle the x. Now we're just looking at this is integrate with the y. Therefore, cy over 2 and 1, 0 equals to 1. All right. So, and then I plug in the y. So y equals to 1, c over 2 minus 0, plug in the y, then I get a 0, and and is equals to 1, and therefore okay, my c equals to 2. Okay, clear enough? So next, okay, for the discrete random variable, we're able to find the marginal probability. We're able to find the marginal probability for continuous random variable. Okay, remember, for the discrete random variable, when I find the marginal x equals to 0, y is changing. Okay, so that's very clear concept. And therefore, when I'm looking for my marginal fx, my y changing, so dy. That's why I do the integration of dy. Okay, when I would like to find the marginal improbability density of y, x is changing, right? Like I mentioned to the discrete random variable, and therefore we do dy for marginal of y. Is that okay? Quite simple to remember, right? So I will give you some example later, but remember this concept. So for the continuous condition density function, the same thing, but you need to find the marginal probability, okay? So like I mentioned to you just now, okay, when for the first equation, I need the marginal probability of okay. So I need this for this part, okay, and okay, I need and this for another part. It's quite straightforward, right? Okay, you understand now? So it's quite pretty similar. Okay. So next we go to expected value. Expected value is mean. Okay. So for expected value, right? The difference is actually you just add the xy, extra xy in front of it. Let's say you have you would like to get the mean of the joint probability distribution, you need to times xy. Okay, I'll give you an example later. For the continuous random variable, for the joint probability distribution, same thing. We add an xy times xy, okay, and add there, and then do the integration. Okay, this is the first. And then once you have done, you use this to settle the integration. Is that okay? Quite pretty straightforward, yeah? Okay, so I show you one example for the discrete random variable. So in this case, draw the mean for the for the probability of xy in this table. So I know that the mean is xy times the fx. So in order to find the mean, I have to times again 2 times 0 times 1 over 36. See, can you see that? You have to do this all in order, and then I give you one more example. 4, another color. 4 times 0 times 1 over 36. And then 3 plus 3 times 0 times 1 over 18 plus 5 times 1 times 1 over 18 plus 5 times 7, no, 5 times 7, okay, 5 times 5 times 7 times 1 over 18 plus, you have to calculate them all in order to get the mean. Yeah, this is the way to find the mean for the joint probability distribution, the mean. Okay. Okay. What about the continuous? The continuous, let's have a look on this example, very interesting. The joint probability density function amount of x of almond and amount of y of cashew nut in a can of nuts was this equation. Okay, so but if you look at it properly, right? Your condition of x is between 1 and 0, but your condition of y is between 1 and 0, and x and y not more than 1. There's an equation on this part. Can you see this? Okay. If 1 pound of almond costs company 100, 1 pound of cashew nuts costs 1.50, and 1 pound of peanut costs 50 cents, then cost of the content of a can is 1 plus 1.5y plus 0.51 minus x minus y, because then equals to 0.5 plus 0.5x plus y. So this is the equation for this condition. Okay. And you know that we need to do the dx first. And we need to find the condition. This is only single when you only refer to y. This is when you refer to x and y. And therefore, you need to move this y. Okay. Let me show you. X plus y equals to 1. So when y equals to 1 minus x. Okay. So it's moving between that range. And therefore, we put this. The limit is 1 minus x to 0. Okay? And we put the equation here. Don't forget. Now, don't forget. Okay? Don't forget. Now, this is to get the mean. If you refer to the mean, okay, if you refer to the mean, we have to put the xy there. Okay, right? So this is one equation. This is two equation. We are joining these two conditions together. So therefore, this is the B equation. This is the A equation. So 24xy and then times this. And if you look at this, I'm looking for the xy. So this equation, something missing. Or are they good to go? No. So we need to add another x, y. We need to times xy. Okay? This equation, something lacking. We still need to times xy because 24xy is for the A equation. And the B equation is this one. So in order to find the mean, we need to have the xy times extra xy. So don't confuse. This is only xy for the A equation. That's why we need to times. Okay, we need to times another xy. Okay, let me write it like this. It will be easier. Okay, like this. Okay, so this is because of the mean. This is because of the equation the B. This is the equation of the A. By putting them, then you can get the expected total value. Okay, this is based on the expected value equation. Okay, so try it out whether it's correct or wrong. Do you get what is your value of the expected value for this condition? We will talk about this next Monday. Let x and y have a joint density function given by fxy is 2x for condition is x is between the range of 1 to 0, y is 1 to 0, 0 otherwise. Find ex. We know that we want to find ex. Okay. Do we mention on that? So if you want to find the joint ex, you need to times xy. What about, I would just want to find the single, how to say that? I would just want to find the expected value of x, okay, from joint density function. you still can find it, but you just need to times x in front. But if you want to find the means of y, and then you times y in front, okay? And still the same, dx first, integration, then dy, okay? So in this case, I want dx and ex, and therefore I put the x in front. My equation is 2x, I put it here, okay? So I do the integration of the dx first, okay? So therefore, I get my expected value is 2/3. You can try the same one to find the EY. Are they the same? Okay. So another example, let's x and y have a joint density. The density. And this time we find the joint density function of the mean of the disjoint density function. So what you need to do is you add xy this time, because you are looking for the xy, right? Same thing, put your equation here, okay, do the same integration. Your joint mean is 1/3. Try it out. Probably I trick you and check my answer. Okay, so now let's move to another part. Is I would like to know whether my event is disjoint, because my condition now is joined by two variables. Are they independent or dependent? So let's check it out. So turn out same thing. If you are independent, okay, PA and B equals to PA times PB. Okay, if they are independent. If they are independent, if and only if when PA and B, okay, equals to PA times PB. What's that means? So I'm sure you did this we learned about this before for our random variable, this discrete random variable. Right. So let's have a look on some example. I think that will be easier for you. So this is the easiest way for you to check whether your system they are independent or not. So for example, this slide, I would like to find px and y equals to 0, okay? And then I find the marginal fx equals to 0. So I know that this one, my marginal x equals to 0 is 6/16. And my marginal y equals to 0 is 6/16 as well. So my fx, my x equals to 0, y equals to 0 is 0. Okay, so this is 0. My marginal 6.16 times 6.16. So are they the same? Apparently they are not, and therefore they are not independent. Okay, if they are showing the same value, they are independent. Okay, let's check it out for the continuous random variable. So same thing like I mentioned to you. Okay, so your you try to get the marginal. So let's say I would like to have you need to find the marginal of the dx and dy, okay, and check it out. So let's say at this part, okay, I try to find my marginal x first, okay, and I know that my condition is between y and x. My x condition is between y and x. My y condition is between 1 and 0 or 1 and x. Okay, so when I do my integration, so I have my 6x, because this is integration of y, 6xy. And I am not sure of the x, okay? I'm not sure, I didn't fix it. You can fix it. So I put it in x, okay? And I have 6x times 1 minus x. Similar, I try to put it in fy, okay? In this condition is y, between y and 0. So I do the integration, okay? Remember, when I do this integration, this is not mean. That's why I don't need to find, I don't need to put x or any value here. So I just do the integration, okay? Check it out first. Who knows, we did some mistake. So this is for mean, okay? When you do mean, you need to add x. When you do join, you add xy. So, and at this condition, we don't need to. So we directly do the integration and you have the 3y squared. So they are not the same. If you can see, they are not the same and therefore they are not independent. So another one that you need to learn is about covariance. Covariance is to show the strength of the linear relationship. So, but it's not showing that whether they are independent. Okay? Okay. What does that mean? So let's say x, y, x. So my line is straight. My line is straight. My line is straight, but they are not y equals to 0. They are not showing they are independent or not. They just show how straight the strength of linear relationship. Okay? So for example, okay, and if my value is positive, it's lie close to a line with positive slope. If my covalence value is negative, it means that I have a line that with negative slope. But if my covalent is close to 0, means they don't have much relationship between them. Okay, but I can't say that they are independent or not. I can only say they are the relationship between them. Do you know what I mean? Okay, so there are some steps to derive it, but the fastest one is this is the covalence equation. The mean xy minus marginal x marginal y. Okay, the mean x and mean y. Sorry, the mean x times mean y. I repeat, the covalence, the equation is mean xy minus the mean x times mean y. Okay, so how this come? This is the derivation. This is the step how you come out this. Okay. Okay, like I mentioned to you just now, yeah, covalence can only show you whether it's strong slope in positive or negative. And with the step that we have learned this one, and also confirm with the covalence, and therefore x and y are independent. You can't just check only with covalence, okay? But if your covalence is equals to 0, and also you check with this, so that is confirmed they are independent. Is that okay for you? All right. So, did I skip something here? Yeah. So in this part, they don't have the range or limitation like the probability, just like that, okay? And there is some condition. If your covalence, okay, you just use the normal covalence. If you have the constant value, okay, so you can bring it out and times the covalent xy. Is that okay? And if you have the two equation, x is the same, and you can use what's that called? Variance to get the x. X and Y independent. If the case is really independent, you will get your covalence equals to 0. But if your covalence is equals to 0, doesn't mean your X and Y are independent unless you test using this condition. Okay, remember this? So this is the example. Consider the following joint condition. So you know that the equation of covalence, let me find it for you. Hopefully I can just, okay. Okay, when we look at the condition, okay, is the mean xy, the mean joint xy minus the mean x and mean y. So for the discrete random variable, we need to find three things. We need to find the mean xy, we need to find the mean x and mean y. Like I mentioned to you, the mean xy is you have to times x, y in front. So for the x, you need to times the x in front. So let's check it out, one of it. So x is -1, -1, 1 over 16, plus you do the same thing. The mean for x is you just put in the x -1 times 1 over 16. Oh, sorry, -1 plus 5 over 16, the marginal, times 0 times the marginal, 6 over 16, plus 1 times 5 over 16. Okay, I repeat, for the mean here, for the discrete random variable, -1 times marginal fx, okay, plus 0 times 6 over 16, plus 1 times 5 over 16. Okay, so you get your mean mean value of x, expected value of x. So for the expected value of y, do the same thing. In this part is -1 times the marginal y equals to -1, 0 times 6 over 16, 1 times 5 over 16. Okay, then you get your mean x and mean y. So your mean xy, you have to use another color. I probably, I don't know, light green. Okay. -1, -1 times -1 times 1 over 16. Okay, and plus -1 times 0 times 3 over 16. -1, 1 times 1 over 16. You have to do all things to find it, and the total is 0. And because the covalent is 0, doesn't mean they are independent. So the best one is you find the let's say EXY equals to are they equals to EX times EY? You have to look at this one. Yeah, okay. If they are the same, yes. In this condition, quite straightforward. We know that E xy same with E. Sorry about this. My pad, my drawing pad is not working. So, oh. Okay. So and this condition, okay, so it happened that EXY equals to EX times EY. So therefore, in this case, they are independent. Okay. So check out in this one and whether they are independent or not. Can you check it out? And we discuss on Monday. Okay, given no, the tutorial is on Thursday, right? Given that xy equals to 2x, when the condition is x is 1 to 0, y is 1 to 0, my f1x is 2x and my f2y is 1. Find the covalence x and y. I know that the covalent is the mean xy minus the mean x and mean y. Right. So how to do this? Can you try? Can you try it? So how to get the mean? How to get the mean? Okay. So first, you know that EXY is XY times the equation. So your equation is 2XY. 2XY. Okay. In order to find your mean x, 2x, y. Same thing with this. So once you put it, you get the answer, you put it inside. If they are zero, they are weak relationship. I wouldn't say they are independent unless you test with this equation. Okay? Unless you test with this equation. Okay. Clear enough? Okay. Okay. It's not that just now what we learned about covalence is covalence to check whether your slope of your equation is positive or negative. Okay. There's another way to check whether they are linear. So it's called correlation coefficient. Correlation coefficient, the equation is covalence over the standard deviation of x and y. So yeah, if x and y are independent, then the correlation coefficient is 0. But the correlation coefficient is 0 doesn't mean that they are independent. It's just like the correlation, the covalence. Okay? So for the covalence that don't have the limit, but correlation coefficient, they have it. It's between -1 to 1. Okay? If your value is -1 or 1, it's showing you it's a straight line. Okay? Whether it's a straight line, positive slope or negative slope. If your correlation coefficient is 0, the relationship between them are weak, okay? Or I would say not much, not strong. Is that okay? Yes. Okay. So this is the summary. The correlation, okay, coefficient is between -1 to 1. If your correlation coefficient is 1, means your slope is positive. Negative, your slope is negative lah. But if your correlation coefficient is 0, okay, you still can't claim that your case is independent. You can only say that, oh, they have a weak relationship. Unless you test, like I mentioned to you so many times, okay, you need to test using this equation plus the correlation coefficient, okay, then you can confirm it's independent. Remember this, okay? Okay, so I give you one example. Okay, calculate the correlation between the two tire experts. We used this example just now, right? So, and if not mistaken, this equation we learned before, okay? So, in order to find the standard deviation, yes, you are using the equation on this, okay? Find the mean of x, find the mean of y, okay, and then find the covalence. Then you put it in the equation here, and then you can get the correlation coefficient. Don't panic, okay? Don't panic, okay? Most of the equation given during the test, it's just you need to remember. It's okay that you can't remember most of the equation. You just need to remember in what condition you need to use which equation. That's it. Okay? It's just like in which condition you need to use which type of shoes. The concept is the same. Okay? Right? So like covalence. What is the equation of covalence? We go back to the covalence. The covalent is the mean xy minus the mean x and mean y. And therefore, that makes sense. We have the mean x and mean y. We need to find the mean xy. Okay, to find the mean xy, so 1 times 1 times 0.1 plus 2 times 1 times 0.05 plus 3 times 1 times 0.02, and you add all of them. This we have discussed this here, page the slide of 33. Is that okay? So once you have the covalence, it's better for me to just copy if I'm able to. Okay, hopefully I can. Okay, I can do this. So oh, not this. Okay. Okay. So the covalence equation is this one. Okay. The covalence equation is this one. Okay. So in this case, we need to find the EXY, right? And given X and the mean X and mean Y already, you can find again, who knows the value is not the right one, okay? And then we can find our covalence. But with that, we can't get our correlation coefficient yet. We need to find the standard deviation. Well, this one, you have to refer back to the previous slide. Sorry, I didn't attach here, but you can find in our previous lecture to find how to get it, okay? Okay, so by putting them, you can know your value of your correlation coefficient, and that show you the linear relationship between x and y. It's not showing independent or not, okay? Yes, all right. So there are some multiple variables So we are not covered on this. So you can further refer to some of the reference, but by using the bivariate, from there we can actually further using with the multiple variables to find the mean. Same concept as above. Okay, so what we have learned today, it seems very long lecture, but it's actually quite simple. We learn about the condition on the discrete random variable or continuous for the join. They are still using the 0 to 1. The cumulative is 1. And we learn about marginal. Okay, so marginal is, for example, I look for the y. The x is the variable, so x is the one changing. And if I look for the marginal x, okay, x is the one fixed, y is the changing. That's why the yellow vertical column, yellow column is the marginal of x equals to 0. Okay, then we also learn about the condition. Same thing, the difference is we use the y. In this case, we're using the marginal. Okay, we're using the marginal probability to in this case. Okay, so we have learned some example together, and also we go to the continuous bivariate distribution. So same thing, they have the same condition. And remember, the continuous bivariate distribution, we need to do the integration of dx first. Once you completed, then only dy. And of course, you can do the differentiate it, and you find back your probability density function. Okay, so, and also, we also learn about how to get our marginal probability density function for CRV. So remember, when I find the marginal x, I know x is fixed, y is changing. Therefore, it's integration with dy. My y, I want marginal of y, but my dx is changing. Therefore, I do the integration by dx. Okay? Pretty simple. Same thing with the conditional density. So we also using the marginal. Okay, we're using the marginal. Okay, to for the conditional. Okay, and if we want to get the expected value, so it's quite pretty straightforward. You just need to times xy with the equation, do the integration. For the CRV, for the DRV, you just refer to the table, like slide 19. Then we talk about some example on it. Don't forget to try to check whether my answer given is correct. Then we need to check whether our sample are independent or not. So the only way to check is the value of probability A and B should be equals to probability of A times probability of B. Okay, slide 25 showing you the general summary. Okay, for the CRV also the same thing. Okay, you times them. Okay, then yeah, so probably you might be confused. Okay, if you look at this probably, okay, slide 25, right? We are using the marginal probability, okay? For the CRV, we are using the marginal probability to times, okay, to check whether they are independent or not. So there are some example in the slide 27 and 26. Check it out. And we also learn about two more things: covalence. Covalence is to check whether your line is positive slope or negative slope. They don't have a limitation on the value. And the next one is correlation coefficient. In order to get correlation coefficient, you need to know about covalence. So the covalent equation is the the mean xy minus the mean x times mean y. Okay, and the correlation coefficient need to divide it by the standard deviation of the x and standard deviation of the y, which you can refer back to our previous lecture for the equation. So there is one equation here. You can check it out. Okay. Example in slide 37. Okay, that's it. So I hope you understand and try the example again. We'll discuss on Thursday, not Monday. Monday is the lecture. Thursday is the tutorial. I will record the answer for the senior. Don't worry on that. All right, see you. Bye.